Show the
Josh, don't be right. Look.
Hello! Hi, this is me teaching D period class, right? This is me teaching D period class. And you're gonna watch this video and learn from it. It's like McMurdo-Minnich, okay? So, what we're gonna introduce today is something called, I know, it's okay, is rational functions, which is a very simple idea with very complicated outcomes. So take out your notebooks. That means you F period and B period at home. Take out your notebooks and we're going to write down the definition of rational function, which is a very, very simple idea. Right? It could not be simpler. Well, it could be if it was a power function, but it really is. It could not be much simpler. The definition of a rational function, as you would expect. What word is in the middle of rational?
No.
Ration, but even better.
No.
Ratio. Right, so this is the ratio of two functions. What kind of functions do you think it's the ratio of? Maybe quadratic, but more generally,
Power.
better, bigger, polynomial. Right?
Yeah, it's glaring too much. I don't think they will.
Can you read it?
I can see it. Kind of.
You think it's readable?
Barely.
Yeah.
Okay, can you zoom in for me?
I don't know how to zoom
Want
in.
me to be your cameraman?
I can do it.
Yeah. Is that zooming in?
Yep.
Yeah.
Go too far.
A little bit
No,
Why
better.
don't you just post
There you go.
pictures to accompany?
No, I like this. Is it visible? Can you see what?
Yeah, you're good.
Okay.
Yeah. And there's that
That's
weird
fine.
scroll
I'm gonna come
line.
in. Okay, so very simple idea. This function is the ratio of polynomial functions. So we're going to call rational function r of x, very clever of us, equals p of x over q of x, where p and q, different than the p of q and our other thing, are are polynomial functions. So very, very simple idea. All right, we're just taking two polynomial functions and we're dividing them. Now, the long run behavior of these functions is very simple. The short run behavior gets very complicated and we'll spend some time on Monday going over that. Okay, so that will be for next week. Okay, but today we're just going to look at the long run behavior. In other words, what happens in the big picture here. So we're not going to look at specific happenings, we're going to look at the big picture. That's still zoomed way in.
Yeah.
I'm gonna zoom out. How's that?
Yeah.
Are you gonna edit this?
Nope. This is raw. I don't have a video editor, so. Okay, so. Are we ready to move on?
Yeah.
Everybody got the notes? Let's look at an example of this type of function. We have r of x equals, let's see, what example do I want to use?
Could r of x equals 1 be a rational function then?
Not really.
What if it was like x squared plus 2x plus 1 over x squared plus 2x plus 1? Would that be 1 over 1?
Is
One.
I mean, technically it could be a rational function, but usually the denominator cannot be a constant. Actually, the denominator cannot be a constant.
It takes a while.
What are you talking about?
But it wouldn't be a constant. It would
What is my
be.
phone?
It would be a second equation, just the same equation.
Oh, then it's
So
just
the same
one.
equation divided by
Boring.
the same equation.
Trivial case. Yeah, boring. Okay, so let's take a look at a rational function like this. It looks pretty complicated, Birdie. It looks pretty complicated. We have 6x to the fourth plus 2x, whatever, 2x squared. Doesn't really matter here. Minus 1 over 5x squared minus 2x. Now, I will tell you right now, your calculator is not going to be very helpful in graphing these. It has a very difficult time graphing rational functions because they have asymptotes. So you're going to need to know what these look like without a calculator, which is actually not that bad. What do you think is going to happen here in the long run? What do you think this function is going to look like in the long run? In other words, zoomed way out.
That.
Oops. No, that's some other function. It's something similar, yeah. Okay, so 6x to the 4th plus 2. What happens to the top in the long run, guys?
It becomes larger than the bottom.
Well, that's true. And what power function does the top act like in the long run?
It's a
6x to the 4th. Good, Chelsea. Right? And how about the bottom one?
Also u.
Just 5x squared, right? So both of these act like U-shaped functions. So if this thing eventually approaches this, right? Leading term, what does the whole thing eventually approach?
6/5 x squared.
6/5 x squared. So the general shape of this is going to look roughly like a parabola. With some holes in it. Allie, put that away. Gosh, preserved on video forever. Me yelling at you.
Birdie took like over 1,000 photos on their phone.
Good. Okay, so 6/5 x. Let's take a look at this in the calculator. Or something similar at least. I don't remember if I have this exact same function. Oops, I don't have anything close to that. Okay, 6. Oops. Be careful with your parentheses here. You need to group the top and the bottom together. 6x to the 4th. What was it?
Divided by 5.
Wait, what?
Plus 2x squared. Plus 1.
Minus 1.
Minus 1, thank you. Doesn't really do much. Divided by
5x squared.
Divide squared. Notice I have to group these. Oops. I double divided.
Is that a bad thing?
Yeah, that would be bad. Can you see this on this thing? Probably not.
No, not at all.
It's even lower.
Now you can.
There you go.
5x squared, what was it?
Minus 2x.
Okay, so we're going to graph this. We're going to see what it looks like. Who's graphing the standard window? No. Uh-oh.
It's angry.
Uh-oh. So, some good things happen here, some bad things.
Looks like
we see kind of a parabola shape, right?
There's an asymptote.
There's an asymptote. So we have 6/5 x squared, we said it would look like, right? Group that if we want to, it doesn't really matter actually. Okay, if we graph this, it's roughly going to fit the shape of this function. Agreed?
Mm-hmm.
What do you think happens if we zoom out even more?
And then the same.
Pretty much.
They become even
Just
more.
all the same.
Let's zoom fit this and see what it looks like. Okay, there's my first function.
You still see it's.
Yeah, it
see
does
a
look
little
funky.
bit of.
And there is my second function.
Whoa.
Are they the same?
Pretty
Pretty
much.
much.
No, but they're very, very similar, right? And so this is long run. Notice this is actually not even that big of a window. It's just from -10 to 10 and from -8 to 125. We can make this window much bigger, right? We can make it to the thousands or the millions or whatever, and it would be much closer together. Okay, so what is going on here with this graph in the short term? Let's just do the f of x by itself.
It's got a negative growth. It's got a stem.
Yeah, it does have kind of a growth. Now, what's happening here is that we actually have an asymptote, as Josh said earlier, right? But the calculator does not do a very good job displaying asymptotes. It tries to connect them.
Wait, so it
Which is
shoots
bad.
down forever and then
It does not. It actually goes like this.
Sick.
So it's like a little.
Something like that. It's actually a little different than that, but it's close enough.
Then why is it going negative?
Because, like I said, it tries to connect the two sides of the asymptote. It tries to bridge the gap, which doesn't work very well. You can do a couple things to make this look a little better. If you go to mode and change this to dot mode, it sometimes turns out a little better, but not usually that much better. Then you get a series of dots, which aren't as connected. So you can kind of see this here. This does actually go a little bit below here, but in general it works like that. So dot is not that useful, sadly. Actually, that's yeah. Okay. So it's hard to graph these on the calculator. But in general, what I want you to know here, right, is well, we're going to work on the other part later. What is the general shape of this function?
Problem.
A parabola. Why?
Because the ratio is more or less.
The ratio of what?
The highest powers.
The ratio of the highest powers of the first degree term, right, it determines the overall shape of this function. Does that make sense? Because in the long run, right, these two polynomial functions just act like they're leading terms. Okay. Now, what we'll look at next week, and for most of next week, is how do we determine the asymptotes and the short-run behavior. Okay. Let's look at an example of a polynomial function that we're going to have to put together here. We have free homework problem.
Which one is this?
Number 1. Okay, is this a polynomial function? As written, does it appear to be polynomial?
Yes.
Does it look like does it look like a rational function, I mean?
Yeah.
Kind of. What do we really need to have though here?
1 over x, which
1 over x is rational, which is okay.
you need to make like bases.
Yeah, common denominator. What's our common denominator going to be here, guys? 2x, right? So we need another x here, another x here, we need a 2 here, and a 2 here. Okay, so that's going to give us x cubed over 2x plus 2 over 2x equals x cubed plus 2 over 2x. Is that a rational function?
Yes.
Okay, are both the top and the bottom polynomials? Yeah. Okay, what is this going to look like in the long run?
A parabola again.
Yeah, long run, this looks like x, so we would say as x approaches infinity, or negative infinity. What does this thing look like?
Pop x squared.
No. Yeah, it's close enough. I'll fix it. I'll fix it for you guys. Okay. So, long-term behavior looks like a parabola again. Alright, makes sense. We have the difference here of 2 in terms of degree. Now, if we look at this, what asymptotes will this thing have? What are we going to have for asymptotes?
0.
X cannot equal 0, right? We know that x cannot equal 0. Why not? Because 2 times 0 in the denominator is 0, right? And that gives me a denominator of 0, which is bad. So x cannot be 0. What does that tell me? What am I going to have? It's going to be 2 separate parts, right? It's going to have a vertical asymptote at 0. Okay? And if we graph this, we'll see that. This is a funky looking graph. Again, because the calculator hates us. But basically, it's going to look like this. Something like that. Pretty cool.
And those lines are
They are
going
approaching
up
vertical.
ever closer.
Exactly. This isn't a vertical asymptote, so these lines are going up and they're always getting closer to the y-axis. As x approaches 0 from both sides, right, this line gets closer to the
So if you
y-axis.
zoom in, it would look like a W, right?
Kind of, yeah.
Yeah.
Yeah. I'll show you what this graph looks like. It doesn't come out very well. So the calculator is rendered useless, a very expensive piece of junk. I'm not sure. I haven't looked at the iPad programs. They may work a little better. I don't know. So let's render it as, what was it? X cubed.
Over 2.
You can see here, we have trouble with this asymptote. Bad. This should go back up.
But that one on the
But
right
it
isn't too
shouldn't
bad.
really go back up.
It's not too bad.
It really shouldn't go back up at all. It should just stop, right?
No, because as your x gets closer to 0, then from the left-hand side or the right-hand side,
Yeah.
right, our whole thing starts to approach infinity. Because think about what's going to happen here.
So the
Right, if
actual-
I get a very, very small x here, what happens to my denominator? Small x
Goes away.
makes my denominator small, right? If I divide by a small number, what happens? Big number. So it goes up to a positive infinity.
Oh.
Okay?
Wait, is the horizontal line another asymptote?
Uh,
I mean,
Are they ever going to meet? The double?
No, they'll never meet. It's going to be, that zero is going to, they're going to approach zero but never get there. So they're going to squeeze in closer to that y-axis but never quite get there. Okay? So we'll examine the asymptotes a little more. I do want you to have some practice with, so some of the problems I'm going to give you are practice with working with rational fractions or algebraic fractions. We did this in the inverses. You guys are actually pretty good at this, if you remember, right, when you had like the rational fractions or algebraic fractions and you had to write the inverse for it. It's pretty easy, yes.
Why should it go up again?
Oh, maybe it does go negative.
Because when you put in a
Yeah.
really
Oh yeah, you're right. You're right. If I put in a small number, it's going to be a small negative number. It would be
Yeah, because it's close to 2, so it's positive again. When you put in a small
right. No, I agree. And then it's going to turn negative. You're right. No, Ferdy's got a good point. So this actually does not go up again. Calculator did not break. That's good. So this does continue down. So the asymptote is still at 0, but it's heading down on this side. Crazy. Thank you. That's bad. Bad math by me.
So,
Good job,
would
Brady.
that be the same?
I was thinking of the fourth power, which doesn't do that. Fourth over second. Okay? So pretty cool stuff. These graphs are awesome. They are really cool looking. They look like amoebas or something. Okay? Any questions? F period, any questions? Too bad. And B period too.
Hi, people.
Give him a smile.
Oh, nah, it's too late now.
No, wait.
They just got beer.
You still recording?
They just got beer.
Wait, didn't I press the recording button?
No,
Oh.
they're gonna ruin
Honestly,
my post your
stupid.
shirt.